see this. Okay, we want to recap. Um, how to make it smaller? Okay. So I want to recap about protein purification. Hmm, best video before you start doing your purification. Okay, protein purification. So it's a process of protein separation. It's a process to separate the okay process to separate uh, your target protein from the impurities. So first you need to know about the molecular weight,
Doctor,
charge of the yes.
uh, are you sharing screen or
No,
just
I'm
voice?
still writing. Yeah,
Oh,
just
okay.
voice. I'm still writing on the my whiteboard.
Okay.
Yeah, so I'm writing on my whiteboard and then I'm looking at the slide. And then we have solubility, and then affinity. Okay, so this is what we have. I don't know either you can see it is a mirror image or just normal image from your side. Is it normal mirror image or what from your side? Okay, because from my side it's just like a mirror image for me. Okay, so we have before we start to do purification, we need to know all this four. This is really important. So we need to know molecular weight, charge, solubility, and affinity of your target protein. Okay, so we cannot just blindly go and then say that we want to purify the protein. And then what is the size of the protein? I don't know. What is the charge of the protein? I don't know. What is the solubility of the protein? In which buffer? I don't know. Is there any affinity towards your protein? I don't know. So meaning that you have nothing to be purified if you don't know all these characteristics. Okay, in case you are given a topic where you need to purify a protein of interest, for example, if you want to purify insulin, you want to purify insulin from one organism. Okay, so if you know that you have one insulin and then insulin which come from different type of source will have different characteristic. But at least if you have got the insulin from, for example, from this kind of human, okay, or mammalian cell, so you need to have an idea. You need to read what is the characteristic of that particular insulin from that source. Okay, if you're working with the enzyme you want, for example, you want fructose. What is the simplest enzyme? I can say okay, alpha glucosidase. Alpha glucosidase from um, from geobacillus. Okay, geobacillus and bacillus they are almost similar. So that means you need to read more about um, alpha glucosidase enzyme from geobacillus and bacillus. Okay, read from the paper, the published material. So what need to be recorded? You need to observe on their molecular weight, solubility, and then as well as its affinity. But affinity is really subjective. If it is if that only alpha glucosidase, so If it is not a recombinant, that means there will be no affinity towards something. But at least you get to know the molecular weight and the charge of the protein. Okay, so you have Geobacillus type A, but still from Geobacillus sources. One of the Geobacillus sources, that means it will share almost similar characteristic. You don't want to read that alpha glucosidase from higher eukaryote, or yeah, or maybe from the any fungi or eukaryote, because Geobacillus is prokaryote. So you want to read Geobacillus alpha glucosidase from Geobacillus. Okay, that's the way how do we start our experiment if we do not have any idea what is our molecular weight, what is the pi of the protein. At least, for example, if you read um, alpha glucosidase from 30 different type of Geobacillus or Bacillus, then you will have some idea. Okay, basically from the Geobacillus or Bacillus, it will have um, this range of molecular weight and this kind of pi. Okay, I cannot share the screen, but at least you will have some idea. If Geobacillus alpha glucosidase from Geobacillus, the size will be around 50 to 65 kilodalton. So you know from that 20 or 30 Geobacillus species, you know that alpha glucosidase from this species, the size is range from 50 to 65. Okay, so you know what to expect for your own Geobacillus. Okay, even for PI or charge, you will know based on the reading that you have done. So if the size give you, if the PI telling you that from these 20 Geobacillus, the PI is around 5.6 to 7.3. So you should have this idea that your alpha glucosidase from your type of bacillus just now will have this range of PI. It will not suddenly, okay, mine will be 9.6 PI. So that's totally up from the range. Okay, this is the way how do we start with our experiment. Of course, we don't know much about the one that we have collected, but we should have this literature review or idea from the um, research conducted by other people. Okay, so that's the introduction. Okay, what is so important that why we need to know about all of this. Okay, so we know that we have done the I will grab my wait. Okay, okay, so we've done the okay, so we have technique. So we have done the gel filtration or size exclusion chromatography. We have done the affinity chromatography. We have done the IEX. Um, HIC, we have not done it. And then even dialysis is part of the science exclusion chromatography, but we are going to include this dialysis. Maybe another one will be um, salt precipitation. Okay, so we have this. protein separation technique. We have done the gel filtration, also known as size exclusion chromatography. And then we have the affinity, the one that we have done in the lab. And then we have the IEX. We have not done this HIC, but it's almost similar to IEX. And then we have this salt precipitation. We haven't discussed about this, but you have known about this during your biomolecule class last time. And then we have this dialysis. Okay, so um, let me try undo. Okay, still browser cannot share your screen. Okay, bye bye. Okay, I'm going to invite this. I'm going to invite so that I can use the screen, whatever happened. So let me try my own email, the Gmail here. Mm, okay, join meeting. I'm going to use different platform. I will turn off the video for a while. Join now. Okay, I have my dummy account. Okay. Um. Oh no no. Okay. Can you hear me? Okay, this one works. Um. Yes. Can you see this? Um. Exactly. The screen.
Can see, doctor.
You cannot see.
Can.
Okay, yes, can.
Okay, I will terminate from this one. So I'll be using this. It works. Okay. Thank you, Hafiz. So I'm going to present this. Okay. Um, so we have discussed about this. The heavier protein, will come out first, and then the lighter protein will come out later. I don't know if I make it like this. Can you see the slideshow? If I make it in slideshow?
Yes,
Yes.
clear, doctor.
Okay.
Yes.
So yeah, we have discussed about this. Heavier protein comes out first, lighter protein comes out sooner. Okay. So if you look at this, we have the we discussed about 280 absorbent and 410. 410 here, the black square, okay, point. This graph basically tells us about the activity. I mean the activity of that enzyme. Okay. I kind of okay. So it is an enzyme which used for molybdate degradation. Okay. Okay. It's another type of enzyme. Okay. It used to degrade molybdate. Okay. So for this part, if you can see here, the 280 nanometer, it's just like this point. If you don't have the the 410 reading. Okay, you can see the rhombus side here is just low. And then you can also see another peak. There are two peaks here at fraction number 40 and at fraction number 55. Okay, it's obvious. The peak start to give, I mean, not really sharp peak, but still there's some protein there, starting from, oops, peak number 39 until tube number 68 or something like that. Okay, so what happened here? They measured the activity of the molybdate by using the absorbent 410 nanometer. So it tells us that at fraction number 40 and fraction number 55, this is the two highest peak. Okay, two fraction with the highest activity for the molybdate at 410. Okay, so if this kind of result we can see, okay, from fraction 40 and fraction number 60, okay, normally from 40 to 60 there are 20 tubes, 20 fractions. Normally we will take all these 40 fractions, okay, all these 40 fractions to be proceed to the next step, or we can even choose I want only 5 fractions from 40 and then another 5 fractions from 50 to 55. That's it. It depends on our justification. Okay. So the one that you pick, I mean the fraction that you collected, this will be your pool fraction. Pool fraction meaning that it is a POOLED. Okay. It's a fraction where you collect or you combine this all fraction, and then you can calculate the total activity from this fractions. If you have collected the fraction from 40 to 60, 40 to 60, and then each fraction, okay, each fraction you dilute with 2.5 mil fraction. 2.5 mil from fraction number 40 until 60, meaning that you have 2.5 mil times 20. Okay, meaning that you have 2.5 mil times 20. Why 20? Because you have from fraction 40 to 60. 40 to 60, that means you have 20 fraction. 20 fraction, and then each fraction you have 2.5 mil. Okay, 2.5 multiplied by 20, then you're going to have how many mil? Okay, mm, 2.5 multiplied by 20, you are going to have 50 mil. Okay, if you have collected 2.5 mil for 20 fraction. Okay, so this 20 mil, you can proceed with the next activity. What is your next activity? You may want to do IEX. You want to do the IEX. Yeah, you want to do the next protein purification, which is ion exchange chromatography. So that 50 mil, so you need to adjust either you want it to be positively charged or negatively charged. Okay, that's why this is where your your what we call it, um, your PI is, if you know the information about your PI, this is where your PI takes place, where you can prepare your protein to be positively charged or negatively charged. Okay, and then from that IEX, okay, we have discussed about IEX before. Um, Maybe from IEX you have only 20 mil active fraction. So from that 20 mil, what's next? If your 20 mil give you really good band of protein, like single band, like the one that you did for your affinity last time, then that's enough. But if from IEX you still can see a few other bands, okay, you may want to proceed with the next step. So imagine for the first step, you do gel filtration, second step, you do the IEX, third step. Maybe if you require HIC, then you need to do HIC. Can you imagine every step you've gone through? You have lost your protein. Okay, so yeah, and but the fold will be increased. Okay, because your protein become purer than before. It's more pure than before. Okay, so um, any question for that part? Okay, you have. I'm still sharing my screen. Can you see the screen?
Yes, doctor.
Okay. Um, so that's why when we do the gel, I mean let me check on this purification table. Okay, so if you have this, then you can see, wow, there are many steps involved in purification. So, um, yeah, maybe this one. So it start with crude extract, which is your first one, crude, and then
Doctor,
maybe it choose, yes, you can see now.
I I only see the gel filtration slide.
Okay, I'm going to share again. Stop this. Share your a window, maybe a window. Where to go? Okay, can you share your own screen? Can you see now the
Yes,
purification table?
purification table.
Okay. Okay, so I'm not going to make it bigger. It's just like this size. I think you can see clearly. So if you see here, crude cellular extract, meaning that the one that you extracted, okay, the first volume started with 1.4 liter, 1,400 mils, okay, 1.4 liters. So with this total number of protein, total number of activity, with the specific activity is only 10, and then the yield is just 100. Okay, it started with 100%. And then second part, you choose salt precipitation where it involves sorting in and out. We can see this later. And then after salt precipitation, instead of 1.4 liter, you have reduced to 280 mil. Okay, it's a big reduction from 1.4 liter to 0.28 liter. And then the total protein now you have only 3,000, where many proteins have been removed from from the solution. And then the activity now you have lost a bit, at least 4% you have lost. Okay, you have lost from 100 to 96. So this is really good. You managed to reduce the volume, but the activity still remain there. I mean, still active and still in the tube. You have not discarded all of the protein. I mean, most of the protein still in the tube. And then specific activity is increasing because you have reduced the amount of protein. Okay, then from this, you manage to get the ion exchange chromatography. You want to proceed with amino sulfate, ion exchange chromatography. Okay, so from ion exchange chromatography, the active fraction, the tube that has the tubes that have the the peak and the activity of your protein, the total volume is 90. If you have one tube with 10 mil, wow, that's a lot. Okay, that's ridiculous. 10 mil, maybe you have one tube with 5 mil. So 5 mil, maybe you have 45. No, 5 mil divided by, okay, 90 divided by 5. Okay, if you have 18 tubes, okay, for ion exchange chromatography, when you have the peak after the illusion, when you start to apply your high salt concentration with a strong positive diluted, if you have 18 tubes, 18, 18 tubes, each tube, okay, have 5 mil. So the total fraction you will have will be 90. So 18 multiplied by 5, you will get 90. So this is how do you calculate, you get your fraction volume after IAX. Okay, so if you have 90 volumes, the total protein will be, yeah, of course, reduced because you have remove majority of protein during the flow through. So out of 280, only 90 represent your active protein. And then the total protein from that 18 tubes, okay, is 40. And then the total activity is 80,000. Okay, now you have reduced. Okay, you got 80, meaning that from this 80, how do you get 100 multiplied by 100? Divide by 100,000 multiply by the current step total activity divide by current step total activity divide by multiply by 100, then you get this. Activity is decreasing because you have UX. Okay. Oh, we know the size of our protein.
Doctor,
Now we
doctor,
try to choose
doctor.
proper
Hello, doctor.
pause for the SIC. Okay, proper anion exchanger or cation exchanger. But for size exclusion chromatography, we need to select based on the size available for that. Resin. Total protein here you lost. Okay, you lost more protein here, but that's okay.
Doctor, bayar.
Doktor?
Doktor hilang kan?
Uh-uh.
Kita ingat kita punya internet tau.
Hilang terus ni.
Terus stuck. Macam mana? Doktor. Terus keluar
Lah.
kan?
Nak terus keluar. Tapi
Kita
rasanya doktor explain pasal formula je kot tadi kan?
yelah,
Formula
yang
PCH table. Hello? Apa dia Marina?
tapi tak berapa dengar apa doktor explain tadi.
Itulah.
Hello.
Hello doktor.
Where? Which part?
Doktor?
Anyone? Izati? Can you hear me? Okay.
Doktor,
Dekat
can
mana
you
stop?
so far tadi saya clear dekat 18 times 5 dapat 90.
Okay. Oh, takat tu je. Saya dah ke bawah dah. Tu yang saya
Itulah.
tengok-tengok. Alamak, skrin dah terputus.
Start
Tu
dekat
yang saya
situ
kata
terus
cakap
boleh
seorang-seorang.
berlari.
Okay. I'm going to share again the screen. Share a window. Share. Okay. Here. Okay, can you see it now? Boleh nampak tak?
Boleh doktor.
Okay. So 18, okay, this one IEX. Okay, so 18 times 5 you get 90. Okay, now the volume has reduced from 280 ml volume to 90. Okay, but the total protein, since majority of the protein you have removed during the flow through. So from 3000 you have reduced up to only 400 milligram of protein. Okay. Now, okay, what happened now? Okay, from activity side, you have got 80,000. Okay, specific activity has increased. Okay, so from 30 unit per mg, now it's become 200 unit per mg. Okay, you have removed the impurities about 2,600. That's why the protein left is only 400. Okay, so from here you calculate the yield. So 80,000 divide by 100,000 multiply by 100, then you get the yield. Calculate the activity from the current step, divide by the crude times by 100. Okay, so you have got the yield 80%. If you look at from here, from the crude until the IEX step, ion exchange chromatography step, you have lost only 20%. Okay, still you managed to capture 80%. Okay, so for the next step, maybe they are still impurities there. How do you know there are still impurities or not? Because starting from here to here, you run the gel. Starting from here, from the crude amino sulfate and ion exchange, you run the gel again for the sake of checking is there any extra bands there or not. That's why you want to check. Okay, so you can see that the other bands are removed from the gel. Okay, because you have introduced new step. I mean, additional step to remove the impurities. Okay, so from ion exchange chromatography, there are still impurity. Then you know what are the sizes that you don't want or the size that you want. Okay, you know the size of your target protein, right? Of course. So that's why you need to choose a proper um, metric, a proper with the pores to filter or to get your target protein. So in this case, when you use size expression chromatography, you may want to use the G280 or 275, G um, 250. Yeah, there are many sizes. You need to know what kind of size you need to know. Just like IEX, you choose either you want to make your protein to be positively charged or not, or negatively charged. It depends on the exchanger do you have. It is cation exchanger or anion exchanger. Okay. So for size exclusion chromatography, when you introduce this step, the volume, okay, from 90 you have got only 80. Okay, not too much different basically, because it's just like changing from this to this. Okay, and then after that, the total protein. Okay, this type has given you the protein reduction. Okay, from 400 milligram to 100. So it's good. At least you can remove the protein that you don't want. And then the activity now you have 60,000, and then the specific activity becomes 600. Why? Because you have lost many protein from here to here. That's why the specific activity will be increased. And then the yield, same, 60,000 divided by 100,000 multiplied by 100, then you get 60%. Okay, last but not least, then you know if your target protein having affinity chromatography like his tag or GST tag or maltose binding protein tag. There are many tags available. Okay, so maybe the last step you want to use affinity chromatography. So from affinity chromatography, from the 80 mil of the active fraction, you got only 6 mil. Okay, and then the total protein reduced to only 3 milligram. Okay, activity from this 6 mil, it is 45,000. And then specific activity, of course, it will be super increasing because you have only 3 milligram of protein. Okay, and then lastly, you get to calculate the yield. 45,000 divide by 100,000 multiply by 100, then you get 45% recovery. So what you can say here, based on this purification table, you have started with 1.4 liter, but at the end of the day, you have got only 6 mil. Okay, but the what we call it, the recovery, I mean the yield, the final yield, you have got 45%. I would say this is good because you have lost only half, considering you have done 1, 2, 3, 4. Until the 4 steps, you have got 45%. I mean, that means 55% loss along the way. Okay? So if you cannot do affinity chromatography, then maybe this will be the last step. But still, either you want to proceed with the next step or not, it depends on the purity of your protein, which you have checked using native or SDS page. If it is still not pure, then you need to consider to add more steps. Okay. Okay, so here you can see that you have here one ion exchange chromatography. Maybe if you think that, okay, you have done your first IEX, you need the second IEX so that you can change with the with different cation exchanger and ion exchanger. So the the purification table here will have IEX1 and then second step will be IEX2, something like that. Okay. Okay, so it looks so tedious, right? Starting from the extraction until the affinity chromatography step. It is normal when you are not handling your protein carefully, you lose or the protein become inactive after your third step. It's possible. You have got the peak, but there's no activity at all. It's possible. Or maybe the protein become degrade. Yeah. So what happened? You need to start from the beginning. Start to extract again. Proceed with the first step, second step, third step, fourth step. Okay. And then also bear in mind every time you include additional step, this price will be really high. Okay. As you increase many purification step, every unit of your protein become really expensive. Okay. If you are good in purification later, you can keep optimizing the steps so that you can reduce the number of steps. You don't want the step to be 1, 2, 3, 4. If you can get rid this ion exchange and then still the recovery will be the same, then it will be really good achievement. But if you can get rid of this size exclusion chromatography and the recovery become like 50%, that one is considered double achievement because you have reduced the steps and then also you will manage to increase the yield. Okay. Any question for that side?
Doctor,
Mm-hmm.
just now you said that if the protein has been degraded, we will restart from crude, right? So how we
Yeah,
will detect the protein has been degraded from the activity?
from the assay. Yeah, activity. The protein will always be there because either it is active or not, the protein will be there because you are measuring the protein using Bradford or Lowry, right? So Bradford will measure the certain amino acid and the peptide bond. So either it is um, what we call it primary or secondary structure or tertiary or quaternary, they are still can be measured using Bradford. Okay, but for activity, for the activity, they are measuring only the active form. Maybe along the way you have used a really bad um, I mean illusion buffer. I mean that buffer is super high of salt or maybe high in pH or something that may contribute to your protein to be denatured or inactive. That's why you need to be careful with whatever buffer, whatever solution that you think you want to use. So if it is lost, um, there's a way to get it. Maybe you can refold. I mean, you can unfold the protein. You can make all the protein become all the enzyme become denatured first, and then after that, you can refold it. Refold meaning that you make it active again. You need to do some treatment with the urea or something because some protein they are it is hard to get the active protein. Most of them sometimes like they are formed as inclusion bodies or something. It is always most of the time become misfolded. If the protein become misfolded, there will be no activity or really less activity. So the way to treat this misfolded protein, normally you need to denature the protein first, the enzyme first. After denaturation, then you need to refold. Okay, refold so that um, the protein, the enzyme will fold to its native state, meaning that to the original shape so that it will become active again. If it is active, you put the substrate, it gives you activity. So if it is successful or not, the refolding process is depend on the activity of your protein after that. If you refold, you get the activity again before and after, then you know that okay the process of um, refolding is successful. Okay. So any more questions? Should is it okay a bit now?
Clear,
You can
doctor.
even type. Okay, clear. So this is done for purification table. That's why we want to reduce the steps. Okay, but if we cannot, that's okay. We report this on that. Okay, so because the purpose of this class or the purpose of learning the purification, because we want to know this is the principle, this type of technique, this is the principle. Yeah, at least we okay we know the um, how it works so that we can adjust accordingly to our own protein later on.
Doctor,
Okay, so let me go to
doctor.
mm-hmm. Yeah, mm-hmm.
Hello.
Sorry. Yeah, exactly. Mm-hmm.
Doctor, back to illusion profile.
Mm-hmm.
Just now you were referring on absorbance 410, right?
Yeah,
So I just want to double confirm how to read that
because
again.
410 is the enzyme activity.
Okay.
Okay.
So
Um,
on fraction
okay, that
40,
410. Okay, let me go to this one. I'm going to share the screen for this slide so that everybody can see the window. Okay, this one, right?
yes.
Okay, 40 to 60.
Yes, so between
Hello?
40 to
Yeah.
60, there is 20
Mm-hmm.
fractions.
Mm-hmm. Then,
So what do you mean by we take all
so the
40 fractions to proceed the next step? I don't get that one.
okay, this is where you decide. Either you want to take this 40 to 60 or you just want to take 50 to 60. Only this part. You see, this is the part where you know the size of your protein. Maybe
So we're
in
not
terms of the
referring
activity,
100% on peak, doctor.
yeah, we are referring to the peak also, but we also consider if you take from 40 to 60, then you know that all of them are really your protein. But this is gel filtration, right? The bigger protein will be eluted first, and then the lighter protein will be eluted later. If the 40 is the 40, fraction number 40, is something that within the range that you want, you can take it. Okay, if your target protein, the size of target protein is about 30 kilodalton, you know that whatever coming out before 30 kilodalton is not within the one that you want, maybe you want to exclude that. But if 30 to 60, for example, the second peak here is 30 kilodalton. The first peak is 60 kilodalton. The protein range for your target protein is about 30 to 60. If the protein range of your target protein within 30 to 60, I would say you want to collect all of them. If all of them, meaning that from 40 to 60. Okay,
Okay,
if you know
clear.
your protein size is only 30 kilodalton, you will collect only this. You don't want this 60. Okay,
Okay,
so you need to come up with a justification either you want to take it or not. That's why after your gel filtration, normally you will do you will take a bit just to run your SDS.
okay, clear, doctor.
Okay, this is theoretically will be your second your pick. Okay, so we're done with this. We are going to um yeah. So gel is important, right? Yes.
May I know why we use
Yes,
both?
Amalina.
May I know why we use dua punya absorbent 280 and 410?
Okay, 410 here represent for our case we represent this as lipase activity absorbent, which is 715, right? 715, right? For lipase activity, and then 280 is the protein absorbent. 410 is for uh, enzyme activity. For our case, in our experiment, we will use absorbent 715. Or for us, we will just use simply the second axis. With the library. This protein, this example, is for molybdate. Okay, molybdate. Um, wait, let me grab this. Molybdate. 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 Okay. 10 nanometer. Okay. I'm going to stop sharing this one. I'm going to share this window for the molybdate. Is this molybdate or not? Can you see, Nani?
Kan doktor?
Can you see? So you can see here, data supporting spectrometric blah 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 by complex reaction ammonium molybdate at with ammonium molybdate at 410. So this is for this kind of protein enzyme. Okay, So 280 is for your protein. 410 is for the molybdate. Molybdate. Molybdate is the name of the enzyme that they are working on. Okay. So for our case, we have 715 nanometer, but we do not plot the 715 nanometer. We plot the lipase activity, but the lipase activity is translated from the 715 nanometer. Okay, is it okay, Amalina?
Yes, doctor.
Okay, so okay, we're done with the. Okay, I will stop sharing that one. We go really fast for the second part. Stop presenting this one. Okay, so we have done the 2D right before, right? Do you have any comments about 2D before? Or can we just see the second part, last part of purification, where we are going to see the protein separation really fast. Okay, another thing I want to share, we have decided that I will not take the analysis of biomolecule class next semester. That means Dr. Shafinas will take over the class. And then plus we are not going to have a wet lab until next year. Okay, by the end of December, we are not going to have any lab. So um, hopefully I can share with you, I can help you guys with the analysis of biomolecule class for the biochemistry student for the bioinformatics section. Okay, for the bioinformatics part, I will take over that class just to help the lecturers in that class. We're going to have Dr. Uswatun and Dr. Shafinas for the analysis of biomolecule, but I will help for the analysis of biomolecule for the bioinformatics session. Okay, so I'm going to make this fast for the final part. Okay, can you see the screen now? Or can you see the screen, guys? Um, Zati, can you see the screen?
Clear,
Basic
doctor.
protein separation.
Yep.
Okay, so for this part we have done protein can be separated with size, charge, absorption factor, stability, and heat stability. Okay, so another part, if we can separate the protein based on the size. Okay, we have discussed about SEC, ultrafiltration, and ultracentrifugation. So ultrafiltration, meaning that, and then we're going to apply the pressure here. If you have your protein with the size of, this yellow size is your protein, meaning that whatever smaller than your protein can pass through this ultrafiltration membrane. So what's left now is your target protein. Your protein with the bigger size than your ultrafiltration membrane. At least at this step, we have reduced the volume. We don't want the volume to be a lot, and then we don't want the small protein still in the protein mixture. Okay, so this one can be considered as first step. Okay, so another one we can use ultracentrifugation. So ultracentrifugation meaning that we have put and 4 hours, maybe 3 hours, 4 hours, 6 hours. So this is really long process. But at the end of the day, you can see the smaller protein will be on the top, will be still floating, but the larger protein will be at the bottom of the tube. Everything will look colorless, everything will look colorless, but at least you know, um, one fourth, I mean a quarter of the protein, I mean at the bottom will be the big protein. If you are looking for smaller protein, that means the top protein, the first half of the protein will be um, taken place by the smaller protein. So you need to know if you want to have smaller or big size of the protein. Okay. Another one is size exclusion chromatography. We have discussed about this. The smaller protein will be in the pores first, but the big protein, the large protein, will come out from the column earlier. Okay, and then the small protein will come out later. Okay, and then we can separate protein based on the charge. Okay, from if we are using the electrophoresis, we have negatively electrode to the positively electrode. Then we have the SDS page just now, right? SDS page is the sodium dioxide sulfate. The SDS will make your protein become denatured, and negative will be attracted to the positively charged electrode. So you can see the protein band separated according to the size. Please remember it is negatively charged, but still it comes with the size. Size, I mean the pores in the gel, the pores in the resolving gel will make or will become the resistant to the protein. Okay, your protein is negatively charged, will attract to the positive electrode. Yeah, it will move down, but it will move based on the molecular weight. If you are small protein negatively charged, it will move faster than the negatively charged protein, but large protein. Okay. So another one is based on the IEX. Now we have the negatively charged bit, negatively charged bit, the positive and negatively charged protein with similar charge to the bit will be move or will be eluted faster. Okay. So yeah, this is separation based on the molecular weight from okay, 10 to 10,000, okay, 10 kilodalton to 10,000 kilodalton. Separation based on electrophoresis, solubility increase. Okay, so this is what we call the solubility of the protein. Protein are least soluble at their isoelectric point. We have it's not easy to solubilize the protein, okay, or cannot be solubilized when the protein is placed in a buffer similar to its pi. Okay, so solubility of the protein will be increased as the ionic strength is increased. This is called salting in. This process is for ammonium sulfate precipitation. We have one of the technique just now is salt precipitation. So salt precipitation, in our case, in the lab, we use ammonium sulfate precipitation technique. Okay. So as we increase the ammonium sulfate in the protein solution, electrostatic interaction between the protein molecule will be decreased. Okay, because at that time protein will just okay. I will just mix together because of the salt with the charge and then everything has helped me to deassociate. Okay, so this is what we call salting in. Okay, so after that, okay, we have here low ion concentration when will be increased as salt is added. This is called salting in. Okay, additional salt ion protect the protein's multiple ion charge, weaken the attraction between the individual protein. Okay, so once the attraction between the protein um, is weakened, that means the solubility of the protein is increasing. Okay, and then we have the second part. Once it reach its optimal, after exceeding its optimal solubility, then we have the phase where the protein become in the process of salting out. Okay, this is where we add more salt. The solubility of the protein will be decreased. Okay, because at this point, the protein, okay, will come together, will be precipitated and become cloudy because the water in the solution um, is the water is attracted to the salt now, leaving the protein to associate by the become together. They will give up the water, okay, leave the water to the salt, and then protein will just be among themselves. So this is what we call sorting out. Once salt taking the water, and then protein will be precipitated, and then it will just the protein will be at the bottom of the beaker or the tube. Okay. So this is Hofmeister series based on anion and cations, the strength. Okay, so for our case, we use strong cation, the strongest cation, which is ammonium. And then we have used among the strongest anion, which is sulfate. So we use ammonium sulfate. Okay. So this is what we call the salting in and out. The solubility of the protein is increasing once we add salt. Okay, this process called salting in. Okay, we can see here. Um, okay, water molecule and protein molecule try to just dissociate. Okay, and then this is optimal where you can see protein they associate among themselves. It is not together. Okay, and then last when we have the sorting out, where we have the water molecule um, attract to the salt, leaving the protein to be clumped together, and then yeah, because there's no water for them. Okay, then this at this stage the protein will looks like cloudy because we have increased the salt concentration. Okay, you can read this. Okay, the sorting in and out. Okay, electric. Yeah, we have discussed about this. We increase the pH, the protein will be deprotonated, and then if we um, decrease the pH, the lower pH, protein will be uh, protonated. Okay, solvent fraction can be lowered. Okay, those also ion exchange chromatography we have discussed. Yeah, the CV and everything, the washing. Okay, affinity we have done. We have done the affinity chromatography. Okay, let's look at this HIC, the last part, and then we're done for today. Hopefully, I'll leave it for Q&A. Okay, I'm going to stop sharing this. I'm going to stop the current one. I'm going to present a window for this. Okay, can you see the screen now about the HIC?
Clear, Doctor.
Uh, okay, so okay, so what happened now? Um, this is your HIC metric, and then there will be salt being used to equilibrate the column. Okay, salt is quite high salt concentration. It has been used, and then after that, this is where the gray graph where you're going to apply your sample. So your sample will bind to this metric. Okay, and then after that, once the binding's done, this is where you start to apply low concentration of salt, the blue color graph. When you start decreasing the salt concentration, okay, this is where your protein will be detached, will be eluted out from the matrix. It's different than the IEX a bit, but it's almost similar principle. But for IEX, you increase the salt concentration so that you will have different ionic strength. But for this case, for the HIC, you reduce the salt concentration so that the interaction will be weakened between the molecule and the matrix. And then after that, the target protein will be eluted at different salt concentration. So the weaker salt concentration will elute the last protein. Okay. So then after that, okay, regeneration time is where you clear all the metric here, just for the sake of to make sure the metric here can be used for the next cycle if you have it. Okay, so it's, it's almost similar, but you can see different pattern of the salt being applied. Okay, it's almost similar if you compare. Okay, if you compare based on the chromatogram, now we have 4 steps, right? You have done 4 purification. I mean the main thing. Okay, HIC, ion exchange chromatography, gel filtration, and affinity chromatography. These 4 will have different principle and then different pattern of the chromatogram. If you just plot by yourself, think, okay, if you have this um, only the graph, you will know, okay, the graph looks like affinity chromatography. Okay, based on the graph, based on the chromatogram itself, you will know what kind of technique used in purification. And then, if you look at the HIC just now, it will give you different kind of graph. Okay, IEX almost similar to HIC, but different salt, reduced in salt concentration. And then you have also the the gel filtration, where you have the long volume first, and after that you start seeing the peak. Okay, so I think mm, yeah, I think
Doctor,
mm-hmm.
so you would like to highlight about the graph shape, is it?
Yeah, because basically when you look at the graph, you will know what kind of technique they are using. So I believe if you compare based on the chromatogram, you will see obviously each graph will have different kind of different pattern of the illusion, different pattern of the sample injection, different pattern of salt being used. Yeah, so but but all of this they are sharing the same principle. First, we need to have the binding, and then second, we need to have the illusion. So first protein need to bind to the matrix. Second part, protein need to be eluted to be able to be eluted from the column. That's it. So
Okay,
we
doctor.
have here, okay, and then stop presenting this. I think this is the last one. Yeah, you see, this is example of the chromatogram. Salt concentration has been reduced in order to elute different kind of protein. Okay, but if your protein is lysozyme, so definitely there will be no activity for lysozyme in this peak, and this peak. If your protein is lipase, sometimes in here, for example, in RNSA, if this is lipase, that means this peak and this peak, they are not lipase. They will have zero activity for lipase, only this smaller peak. So at least peak will give you some idea where to do the lipase assay. Okay, so you will not do the lipase assay at the position where your absorbent 280 is zero, right? So you will do the lipase assay where your activity, when you have the peak, where you want to select the 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 position, the fraction to do the lipase assay. Okay. Um, yeah, even for dialysis, just almost similar to the ultrafiltration just now, you need to have the like a whisking tube so that the smaller protein molecule will pass through the tube, and then what left in the tube only the bigger protein. So this dialysis tube will come with the size also. So it's slow method. It will take you more than 12 hours basically, and then you will need to change the buffer frequently. Okay. So I think that's it for protein purification. The rest you can just practice yourself, I think. So you can type, okay, cannot hear the sound from the video. Okay, done. So any more questions? We are done with our purification topic. And then next week we will do the characterization part. And then maybe we will have a short some quiz a little bit to test your understanding towards protein assay, enzyme assay, and how to use the standard graph, standard equation, and then some, um, I mean, quiz regarding the purification. So at least you get to know in enzymology we have this kind of topics, this kind of calculation technique that you need to master before leaving the class. Okay. So any more question?
Doctor,
Mm-hmm.
how about next week's live session?
Yeah. Next week. Okay. We need to. Okay. I will install the Webex. Like you have suggested just now. And then good thing is I'm leaving to KL tomorrow. At least I will have my own internet connection rather than my hotspot sharing. Hopefully it will be better next session. Yeah. Yeah, I will try. Next week we can have a proper one. So Amalina asked, can you explain about the pig just now? Like Suzanne not appear which pig. Okay. So for the pig, um, PowerPoint slide share. This is the pig. Sorry, this is the pig. Okay, if you can you see the slide now? Um, guys, I'm putting the slide. So can you see the slide? Amelina, is that it? Can you see the slide?
No, I can see your face.
Okay, I'm going to share again. Present now. Can you see the slide now? Can you see the slide
Yes.
now? Okay, so this is the, for example, you have used this HIC. It's applicable to any of the, they have even here, even IEX, HIC, and then gas filtration, right? Gas filtration. Okay, we don't have the gas filtration here. Okay, but there are multiple peaks there. Okay, you have this, for example, IEX and HIC. Okay, for this IEX and HIC, you obviously you have different peaks. Okay, 1, 2, 3, 4, even 5. 1, 2, 3, 4, 5. Okay. So now, if you are purifying the, okay, now we have lipase enzyme. Then you have many peaks like this. You need to know which one is, which peak represents the lipase. So what you need to do is you need to do assay for this peak. Check first peak, second peak, third peak, fourth peak, and then the fifth one. Why? Because you need to know which one represent your lipase peak. Because the from the 280 absorbent, yeah, they give you the absorbent give you idea where which fraction contain the protein. Okay, yes, you have got 5 peaks here, but you don't know which peak represent your lipase. So that's why you need to do assay for the first peak, second, third, fourth, and fifth. If you know that, okay, this peak, the third peak represent your lipase, that means how many fractions do you have here? Is it if we have fraction number 21, 22, 23, 24, 25, okay, in this 25 fraction, each, and not 25, 21 until 25, that means it's only 5 fractions. In these 5 fractions, how many mil per fraction? If it is 2 mil per fractions, 5 fractions, that means you have 10 mil. So this 10 mil from the 5 fraction from the third peak will be used for the next step because you have confirmed this position, this peak is the peak for lipase. This is where your lipase being eluted. So if you have 10 mil there, then 10 mil, you will collect this 10 mil, go to the next step. And then you can do the next step, purification if you want. I believe from this HIC, maybe there are still a few other bands there. But if from this HIC, you can see only one band, which is at your expected size. If the lipase just now is 43 kilodalton, and the band for these 5 peaks, they are all at 43 kilodalton, and then there are no other impurities there. I mean, it is just single band. Then you can stop doing your purification. You can just claim that HIC has managed to purify your protein with the 100% purities based on the SDS based observation. That's it. Okay, so if you have this IEX still, you don't know either this peak or this. I mean, the first, third, you can do this, but this one still in the unbound molecules. Okay, you haven't put the illusion, the salt yet. So meaning that this is the first peak with the lowest salt concentration. So first, second, third, fourth, fifth, sixth. Okay, so you have 6 peak to be analyzed, and then which peak represent your lipase. Okay, so is it clear? I'm going to stop sharing. Okay. Okay, I think any more question you can just type.
Doctor,
Mm-hmm.
for next week's quiz, how do you know the format already?
Next what?
You said next week you'll be having a quiz. So do you have the format already?
Um, maybe yeah. I need time to prepare the questions. Um, they're just like a discussion. We're not going to have like a really serious one. Everybody have this. I just want to know. I just need to know. Do you understand or not? Yeah, possible. I will prepare on the Putra Blast. Let's see. Um, which one will be easier for me to learn really quickly. That's the thing. That's the challenge for us as educator because we don't really like to do online stuff, but now we need to learn really fast. Yeah, possible I will do the Putra Blast. Just yeah, at least you know how to do the calculation and everything. Because by July, by August, right? You need to have your final exam. Have you got the date for your final exam? I
Haven't checked yet.
think yeah, I think it is 18 of August will be the deadline to submit the final marks for enzymology class. That means the enzyme need to be done first week of August, something like that. First week of August or second week of August will be the maximum. I think first week of August. So we will have the at least 2 lectures or 3 lectures for the protein characterization, and then we're done. We're done with the course. So because you have done the enzyme purification, and then the gel also has been covered. Yeah. The medium for final, still online questions. Mm, we will discuss at the departmental level so that everybody, I mean, all the students will agree with the um, format. And no, not agree. I mean, accessible to all students. Hopefully at the same time, because this is e-assessment. We cannot do the what we call it, the exam like we are doing the lecture. You can do at any time you prefer or something. We cannot. Hopefully, right? So I will discuss with other lecturers who also conduct the lab session or something. Yeah, we haven't discussed. We will meet early July, most of us. So I think even for microbiology, you are also taking the practical class, and then for I mean biochemistry, I think you are taking other class too, right? For practical something. So we need to sit down and discuss the best method so that it can be assessed by all the students at one time. We Yeah, because test two is just assessment, but now it's e-exam. E-exam is not just like normal assessment. We need to have a proper panel to check either the question suitable or not, the medium will be used is suitable or not, or something. Okay, so yeah, if there is no more question, I think that's the end. It's almost 2 hours. So is anyone recording this? Who's
Ira,
recording? Is
Shahira
that
is recording.
okay? Okay, I think that's okay. So as for now, today's lecture, you're going to sign the attendance for today's lecture, and then please just ask question, or write something, not only your metric number, just write something or whatever, comments or something, or feedback, or so that it can be improved, because you're going to have another 2 or 3 lectures later on. So that, are you really comfortable with this medium, or do you need, instead of this, I need more time for what? Or each session need to have another 2 class for to repeat the same lecture. So we need all this so that we don't know in the future, right? So we need to know earlier so that it can be fixed for all of us. Okay, so yeah, thank you, Izati. Okay, there's no more. Thank you. Thank you. I can call your name. Anis, Adila, Arifa, Diana, Irfan, Izati, Jaslin, Amalina, Noraini, Shion Ryota, I don't know what's her name. And then Shaira, and Teku Daniel. Uh, Thank you. Can you turn on the camera for one time? You can take a picture, group picture. How to capture? How to capture everyone face?
I can screen capture, Doctor.
Okay, yeah. Okay, just do it. I don't know why it is too big the screen. Okay, can we squeeze to smaller so that we can see everyone?
There's a three dot beside present now,
Okay, and then
and
change
then
layout.
change layout, change into tile.
Tile. Okay. Okay. Now I can see. I don't even know you are Tengku Daniel. Now I know you are Tengku Daniel. Irfan. I can remember your face, but I don't know your name. Um, Izati, of course. Always I see you. Naraini, Diana, Arifa. Okay, hi. Okay, done. Jaslyn. I can't see you. Okay, never mind. We have only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? Okay, so I'm going to screenshot now.
Okay, smile everyone. One, two,
Smile.
three. One, two, three. Okay, done.
Okay, done. Okay, okay, bye.
Thank you,
Have a good
doctor.
lunch, everyone. See you. Bye.
Thank you, doctor.
Okay.